Welcome to the final day of the 2020 ACM Richard Tapia Celebration of Diversity in Computing Conference. We are very happy to have you continue to participate with us in this wonderful celebration. I'm Rob Park, and I have the honor of serving as program chair of the conference this year. I'm a faculty member in the Information Technology program at the Viterbi School of Engineering at the University of Southern California. My areas of teaching and interest are embedded devices and IoT, computer science education, and mobile development. I have been fortunate to have been involved with Tapia for the past 5 years and have loved the privilege of working alongside everyone. It has been deeply gratifying to join the sessions this year and see the wonderful celebration and the result of everyone's hard work. On behalf of the conference organizing committee, we want to acknowledge all of our appreciation for all of our platinum sponsors. Our platinum supporters include Boston University, Carnegie Mellon University School of Computer Science, Cornell Computing and Information Science, Georgia Tech, JP Morgan Chase, MIT Lincoln Laboratory, Qualcomm, Stanford Engineering, the D.E. Shaw Group, 2 Sigma, UC Berkeley Electrical Engineering and Computer Sciences, University of Chicago, University of Illinois Urbana-Champaign, University of Michigan. We also want to thank our platinum government participants, Lawrence Livermore National Laboratory, the National Science Foundation, and the National Security Agency. We also appreciate the support of our many gold, silver, and bronze supporters. The conference would not be possible without all of your support. This conference is made possible by the hard work of so many volunteers. I now would like to take a few minutes to thank the committee members and introduce some of them, and I appreciate their excellent work. The Infrastructure Committee has taken on the heavy duties of coordinating the conference activities. The Infrastructure Committee includes Rose Robinson, Valerie Taylor, Quincy Brown, Brianna Blazer, Patty Ordonez, Jerry Barrett, Makiva Nodden, Angela Nodden, and myself. Let's give a virtual round of applause for everyone's hard work. The program committee also includes all of the co-chairs of the different sub-programs, and I'd like to recognize each of them. My amazing deputy program chair, Patty Ordonez, Accessibility Committee Chair, Brianna Blazer, chairs, Birds of a Feather Chair, Fatima Richmond, Andrea Delgado Olson, Doctoral Consortium Chairs, Jerome McClendon and Tanya Roy, Academic Panels and Workshop Chairs, Adrian Decker, Christian Lopez, Industry and Government Panels and Workshop Chairs, Lynn Riley, Michael Runningwolf, Technical Panels and Technical Panel and Workshop Chairs, Michelle Kinsey, Stephanie Ludi, Student Posters and ACM Student Research Competition Chairs, Khalil Griffin and Jason Grant. Scholarship Chairs, Nikki Washington, Samuel Lubelski, and Kristen Grant. Thank you for all of your hard work and dedication over the past year for these wonderful sessions. Each of those committees I just mentioned have even more members who participated, reviewed submissions, sat in on meetings, and generally were just always available and helpful. And I also want to thank all of you who participated as well. There are so many more people that we would like to show our appreciation to, such as the staff and student volunteers, everyone who submitted to the conference, all of our invited speakers, your presenters of the various programs, everyone who participated in the exhibition, and the career fair, and most importantly, all of you attendees who made this a wonderful program. We know that this year has been very difficult on so many fronts for so many of us, and I'm so touched that this came together. All of you who participated, all of the hard work of volunteers, and it's really been an honor to participate with you. I would also like to thank, excuse me, I'd also like to take this opportunity to personally thank everyone's for your time and excellent work in producing a wonderful program. We will see you next year in September 2021. I will be the general chair, and Patty Ordonez will be our new program chair. Please mark your calendar for September for next year, and I look forward to seeing everyone. You will be in person, we'll be online, we'll be halfway, who knows, but we will be there. Tapia 2021 will definitely be there, wherever it's going to be. I now would like to invite Valerie Taylor to introduce our 2020 Ken Kennedy Distinguished Speaker. Valerie?
So it's a pleasure. And I also want to take this opportunity to thank everyone because it's an exceptional program. And it really takes all of our volunteers and also the infrastructure committee. So it's my pleasure to introduce our 2020 Ken Kennedy Distinguished Lecturer. But first, I want to give a little background about Dr. Ken Kennedy. As he was our keynote speaker at the first Tapia conference that was held in 2001. Ken was a computer science professor at Rice University, very well known for his research in compilers and programming languages in high performance computing. He was a member of the National Academy of Engineering. Ken passed away from cancer in 2007. In recognition of his research and outreach contributions, we have the Ken Kennedy Distinguished Lecturer at the Tapia conferences. And now, a little background about our speaker, Dr. Colin Parris. So it's an honor for me to give this introduction to Colin as we overlapped in grad school at UC Berkeley. And Colin received his BS from Howard University, his MS and PhD from University of California at Berkeley, as well as an MS in management from Stanford University. His career includes 20 years at IBM, where some of his roles were Vice President and General Manager of IBM Power Systems, and Vice President of Corporate Technology, as well as Vice President of System Research at IBM T.J. Watson Research Division. Colin has been at GE since 2014, where he is now Senior Vice President and Chief Technology Officer for GE Digital. He is joining us today to talk about how digital technology will shape the future of business. Throughout his talk, please feel free to enter questions in the Q&A in your Zoom session. We'll have some time after the talk to address the questions. And so with that, I'm happy to turn it over to Colin.
Hey, thank you very much, Valerie. It's my honor and my pleasure to be here. Great. So again, as I mentioned before, it is my absolute delight and pleasure to be here. Valerie asked me an interesting question when we began. She said, what motivated me to go on the path I did around digital technologies? Well, it actually goes back to my early years in Howard. You know, those were interesting times for me. There was one course I remember taking. It was an electronics course, a systems course. You know, in that course, what you did is you took this thing, and many of you may not know it, it was called a breadboard. It's a place that you interconnect transistors, capacitors, you know, resistors and wires together to build projects. And my project that I was building at that time was a simple, at least as simple in those days, you know, home security system. So what you have is you have two wires, and if you disconnected them, an LED should light up, which should, you know, allow you to say, well, you know, this was a connection, a window was open, LED lights up. Simple to say. It takes about 50 hours to do it. And you end up with a board about 8 inches by 10 inches with a massive wires. And if you move it back and forth or shift the wires, something goes wrong. And that was my first journey. At the same time, Intel shows up. Intel shows up with an 8-chip processor, and you stick that on the board, a couple of wires to an I/O bus, that attach to these sensors and these LEDs. And instead of 50 hours worth of work, it took 8 hours. Then when you wanted to add a new sensor and a buzzer, another 10 hours, that could be done in a half an hour. And that was my first exposure to digital transformation. What did I see there? What did I learn there? 50 hours of work went down to 10 hours of work. To add something new took a small amount of work. And I was writing it in software. So I could pick it up and take it to another board and just put it on another board and it would work. That literally blew my mind. And that was how my journey started at Howard. And when I went on to IBM, that's what they were doing, digital transformation, using these computing systems in banking, in commerce, we were doing Walmart and others, and healthcare. Then from there, I went on my journey to GE, and we were doing it in automotive, we were doing it in aviation, we're doing it in rail, we're doing it in energy, we're doing it in manufacturing. This has been my journey for the last 35 years, one of digital transformation, using digital technology to shape the future of business. And that's what I'm here to talk about. So let me tell you how I'm going to proceed. What I'm going to do, if this button works anytime, is to essentially talk about it in 3 ways. I'm going to first start by talking about the forces shaping the business. Anytime you look at a problem, what you want to do is to make sure this problem is a problem that I'm going to solve, because I'm going to put effort into it, but I'm going to solve it and it's going to last, those solutions are going to last years, decades, maybe multiple decades. So I'm going to talk about the forces shaping business right now. I'm going to focus on 2 specific sectors. I'm going to focus on manufacturing and energy, sectors I know about, and tell you what's happening there to show you that the things you do in digital technologies are going to have long-lasting effects there. Then the second thing I'm going to do is talk about the emerging digital operations model. I'm a firm believer that if others have done something before, it's okay to use that. It's okay to learn from them. You make a lot less mistakes, and if you can build upon the shoulders of what they've developed, you get where you're going a lot faster. So I'm going to show you things that are happening in the consumer space that we're going to use in the industrial space. We're going to adapt, we're going to invent around it, but we're going to make sure we build upon that level that's already been built and drive things forward. And then third, I'm going to actually give you some examples of how this actually gets business better. The role of doing all of this really is a business transformation. That really means, how do I improve the revenue you get, improve the profit you get, actually improve the customer response, the ability to react to what the customer wants, to react to the other things in the environment. We're going to talk about what's happening there. And then I'm going to leave you with a few key ideas to reflect on. So with that, let's try to understand the forces shaping the business itself and see what we think about those. So let's talk about the manufacturing space. And every time I think about these spaces, I try to think about them in certain ways, right? I try to think about what are the constraints you have in that space? What are the things that you want to do? What the customer wants you to do? And then what's the overall environmental impact? And then I think about digital, because I've got to start first with the market dynamics. So let's think about the manufacturing space. So some of the things we've got to think about when we think about this space, because usually people, all start in one spot, is what do you want to produce? But you got to think also about what are your raw material constraints, especially for us. We're in the large manufacturing spaces where we're manufacturing jet engines, we're manufacturing gas turbines, wind turbines, large healthcare machines. Materials are a big thing. So raw material constraints are things that we're seeing. Now, even if you go beyond that and you say, let's go to automotive, and you look at car batteries and automotive, some of those raw materials, the cobalt and the other things in them, again, are resource constraints. Even if you go into other environments, everyone is resource constrained because we don't have infinite resources on the planet. And you have some numbers here just to get you that idea. The cost of steel, at least pre-COVID, was going up dramatically. So is the cost of aluminum. That actually constrains the materials and forces you to look at these materials a lot better. We have many discussions about planetary depletion. We are depleting resources on the planet. In fact, there are discussions now about mining asteroids that pass close enough to this planet. real discussions about that, just to get the resources we need. So look at the raw material constraints. The next thing is the efficiency and agility. We have a situation in which, especially manufacturing, people want quite a few things. They want it customized for them. They want it a lot faster. They want it built in certain ways that preserve the environment. They want it built in certain ways that preserve their environment or their use patterns. And you have to think of all of them. I go back to really simple examples, for instance, potato chips. When I was growing up, they came in one flavor. Now I go into the store, there is ranch potato chips, there's taco chips, there's a variety of chips. The very same discussions we have now when you look at people who want jet engines, you'll think they all look alike, but every one of them has a different characteristic, whether it be around what the fuel consumption is, whether it be the thrust, so how far it can fly, whether it be the amount of carbon it emits. There is a variety of different capabilities. It even gets to the point where you want to make these engines such that the mechanics I have right now aren't changing the way they maintain it, because you want to preserve those costs. So there's a variety of different things we want. So you've got to be really efficient, really agile. Second aspect of this, the third aspect is deglobalization. You have many cases in manufacturing where, because of the current challenges between the US and China, you are having to think about two supply chains. You're having to maybe have a supply chain that's much more North American focused, maybe focused out of Mexico or the US, whereas if you go to Southeast Asia, maybe you've got to look at it differently there. If it's not China, maybe it's in parts of Indonesia, it's in parts of Malaysia. So you've got to think about that market dynamic as well. And when you look at all of these, you have a series of very dynamic situations with a series of great constraints. How do you solve that problem? Because if you go to the bottom on the customer dynamics, they all want profit and revenue improvements. They all have to deal with government regulations. They all have to deal with the market as it adapts to what customers want. And the one solution we see that keeps coming true is that of digitization. For two reasons. One is that the fact is the cost of sensors and those capabilities are dropping. The second is that we have structures and capabilities around things known as Industry 4.0 additive, or even better, analytics, that allow you to actually manage these situations. So again, these are the forces shaping the manufacturing markets. Let's look at the energy markets. This will be a lot easier because they're very similar. We have a similar discussion when we start around this notion of constraints. And the constraints then are all about decarbonization. We have a carbon neutrality focus in which we're going to get to that neutrality by 2050. We have to preserve the environment itself. So now that limits what you can do. You want to put much more renewables, but even the renewables themselves, in the making of the renewables, you have to reduce the amount of damaging carbon gases that get in the atmosphere. So that's a constraint. Then efficiency. We're back to the point in which customers want more. They want smart homes. They want homes in which these homes adapt a lot quicker, keep them warmer. But you also want at the same time to use less electricity. But at the same time, you have very dramatic weather. If you look at the last couple of months in California, the heat waves there were profound. Then you look at what's happening in terms of the cold in certain parts of the year. We are seeing very dynamic weather, even more dynamic now in California, but that means that we've got to deal with that. How do we actually go into these energy markets and produce electricity in such a way that you can have enough of it, but you don't overproduce where you're damaging the atmosphere? Then there's a notion of decentralization. So in the environment we're in right now, things are changing. There are people who are putting solar panels on their roof, and so they can generate electricity and consume. We call them prosumers. They're producing and consuming at the same time. There are people who are worried about the fact that their electricity sources throughout the world, and even in some parts of the US, aren't stable all the time. So they're producing their own grids, generating for their use. How do you incorporate that work inside the overall grid or the overall energy market? And there's just an abundance of distributed energy resources. They have these electric cars that are moving around. You have a number of other electrification capabilities that are happening. So very dynamic environment. Again, every customer is focused on profit. Every governments are in there, markets are adapting. And again, you have digitization as being a powerful capability to actually allow us to reduce the cost of these things, but give you more and more new capabilities using analytics, using notions like the energy internet or the digital utility to actually support it. So when you look at these forces shaping these two markets, you see some things in common. You see a very dynamic environment. Customers are demanding a number of things. You see a very dynamic environment, governments and geopolitical impacts, whether it be the government adding new regulations or a China-US challenge. You also see a lot of constraints. You have constraints around raw materials, you have constraints around carbonization, but you also have constraints in the very plants you have. You've built plants that have been there 20 years. You have people who sit in set of skills. How do you actually use that to begin to transform? So what we do now is, as we see the forces shaping the markets, and we know they're going to be around for the next decades, can we look in places where this has happened before and see what they've done and build on their shoulders? And this is the journey we took, and we said, okay, let's take a look at the consumer space. And so I'll talk a little bit about that now. And I'm sure many of you, if not all of you, have had the experiences, you know, with Amazon or with Google right now, or several of you, you know, who have experienced other parts of the world, see it in Alibaba or Ant Financial or Apple. The notion here is that they have been in this digital transformation and they have done certain things in the digital transformation. Can we build on that capability? So let me talk a little bit about what is actually going on there. So whenever you think about digital transformation, you think about two things. One is a business model. One is, how do you create value? And the other one is a delivery or an operations model. How do you deliver that value, right? So let's take Amazon as an example. So what Amazon does in value creation, they do some interesting things. You know, they can normally give you an interface in which you can see the goods that you want, but the real power they have comes from the fact that they can help anticipate what you'd want and get you access to things you never saw before. So you go on the Amazon interface and you type in specific things. You type in, like I did for my wife, you know, I was buying her a camera, one of these very nice reflex cameras. I type in information about the camera and it comes up and it tells me, here's 10 cameras you could select from. It not only tells me that, it gives me a price, technical capabilities, and it gives me a list of customers who have written their own views of it. So there's a whole section in which people have rated it 5 stars, 3 stars, 1 star, and I get to take a look at that. But what you understand is that that is customized for me. Because I play a little game here. My wife also has an Amazon account, and she actually goes in and types in the same camera. Here's the interesting that shows up. The price is different. They have looked at her persona, they have looked at her buying pattern, the price is different, right? The technical specs they give her are very slightly different. And a lot of the reviews are all about the experience. So my reviews were really about, you know, the specifications, right? Her reviews were about the experiences. Look at the clarity of the pictures. Look at the ease of use. Mine are all about, here's the actual speed by which the lenses operate. Here's the size. Now, why is that? That's because they're looking at my buying habits and my buying patterns and what I tend to look for. And they've already calibrated a digital model around me, a twin of Colin. And so they're presuming how I'm thinking about things. And they're doing different things for her. But the whole purpose is to get you to buy. So they're detecting the things that I'm interested in. They're predicting what I'm looking for, and then they're optimizing it. Because usually when they tell me to buy something, they say, and if you buy these other 3 things, you get it cheaper. That's a digital model. That's how they create value. Now, how do they deliver that value? Here's what they do now. Now what happens is, in addition to giving me a nice catalog, when I hit buy, immediately that goes into their supply chain. And what most people don't realize, that initially, if I just buy one thing and it's a thing they have, this goes directly into the supply chain operations. It goes right to the Kiva robots. The robots walk down and grab things off a shelf and bring it back and drop it in a box. In several cases, the box itself rolls down a platform and a robot seals the box and that comes to me. Now, when you have 3 or 4 things, a human gets involved and puts all that packaging inside and balances the box in ways that make sense. But usually, they're doing that value delivery with less and less humans. And that's why when you think about it, they can have 270 million customers. That's why they can get things to you within 2 days with Amazon Prime. So think about that as you look at what's happening. Now, Google does the same thing. When you click on a Google ad, that Google ad is customized for you to get you to click. That's the digital model. That's the business model. The way they deliver the value is they actually, once you get that click, they can route you right away into the store itself, and they can watch what you do there. That's the delivery. They deliver you to the right catalog, the right place. So this is what the consumer world has been doing for years and doing it very, very well. So you see a couple things. You see in the regular models, what we normally would do if we go into a regular store, it's a human process. The human would come up, a human would advise you. You'd go into the store, you'd talk to one of the clerks in the store, and they would say, well, here's the cameras you should look at. And then they may occasionally go and they may actually pull up a, if I said, what about the specs? They may pull up a computer system and actually say, well, here's what the specs look like. That's a human process with digital support. What Amazon has is a digital process. And in that digital process, they do put in human creativity. At times they say things like, well, let's try a different type of algorithm. Let's expose Colin to these adjacent spaces. If he buys a camera, he might buy a camera bag. You know, he might be going on a trip to take pictures. At the same time, let's offer him, you know, something interesting for a trip, like one of these pillows for your neck. And I'm saying this because that's what actually happens when I use the system. So that's a digital process with human creativity. When you look at the regular thing, it's human insights with data. You want a human actually saying, usually humans say, well, let's have the cameras, and next to the cameras, let's have the tripods, and next to the tripods, maybe we have phones if you walk in a Best Buy. However, in the Amazon model, it's data-driven insights. They're watching what I look at, and the next set of things they show me as ads, you know, when I'm buying the camera, show up because of the data insights. And then they use human expertise. At times, they'll ask humans to help us judge that a little bit. Maybe there's something going on in the world right now that is not as part of historical data. I can use other data. The thing with the model that's analog, when you go into Best Buy or you're going to Walmart, there's limited scale because there are only so many things that they could put on shelves and I could look at. When I get on Amazon, it's exponential scale. So if you think about that, what's happening here is that in the consumer world, they have a digital model about how you create value using knowledge about you, using analytics about you. And then there is an actual infrastructure logistic model by which they deliver value, which is a lot software-based, but you still have humans. There's still delivery vans, they still get it in front of your door. And so there is a whole bunch of capabilities that they're using there in digitization. So if that is true, if you can use value creation as they effectively have done, and why I know it's effective, it's interesting. Amazon is roughly about $245 billion. They got to $100 billion in roughly about 19 years. They went from 0 to 100 billion in 19 years. I was with IBM. IBM took roughly about 94 years to get to $100 billion. GE took 96 years. They got there in a much shorter time. You look at how quickly it got Google. Google is about 145 billion in 2018. How fast they got to $100 billion. And it's 3x, you know, or 4x, you know, faster than the regular companies that you well know. That tells you that this combination of business model and operations model can deliver huge value. So what do I do? What do I do is I literally say, how do I apply that in the industrial world? So let's talk about that. So we start by saying the core of this is using that data to get insights, right? And so in my world, right, I'm using the data that I have about building, designing the jet engines, the steam and gas turbines, the electric grid, not only designing them, but I manufacture and I service them and I watch them operate. I'm using that data to build something we call a digital twin. That digital twin is that digital model of how the asset works. Now, what is a twin? When I say it's a model, think about, we all build models, right? We're in university, we build a model. Usually you build a model before you do a design, or if you have a hard problem in services, you build a model. What makes a digital twin different? It is a model, but it is a living, learning model. Because what I do is usually when you build a model after the design and you finish with the design, you don't use the model much. Or if you build a model in services because of a severe service condition, After you fix that condition, you stop using it. This is a living learning model. By living, I mean I'm taking a source of data and I keep updating the model. So the model is an accurate reflection of the asset while the asset is in the field. So I don't stop. I actually continually stream data back, and the model gets that data, the model adjusts itself, so it's a living model. How's it a learning model? Well, I can do learning in a couple of ways. I can use this model and I can say, okay, if I'm getting all this information, about electricity, how about if I try something? How about if I try to predict, maybe a day in advance what electricity usage or demand might be? And so I can use my sensors to try to predict, well, given it was this way, what would it be in the future? I can do that. Or I can say, you know what? I know what's happening to some of the parts there. Can I maybe predict before the next repair or next inspection interval comes a month down? Can I just predict what they would find when they do that inspection? So I can actually use my data to predict something and then see how good my prediction is and get better. So I can use my sensor data to learn. I can also use the fleet to learn. Can I look at other machines out there that look like me, that have been running for 2 years earlier than me? And can I learn from them? What kind of damage they've seen? What kind of performance they've had? Can I learn from the fleet? Can I learn from simulators? We build powerful simulators, especially at the large, US government labs we have. Some powerful simulators based on huge supercomputers. Can I use those simulators to learn from them so I don't have to learn it in the hard way? I can do some extreme conditions. And can I use humans? Can the humans, because they've designed the machines, tell me things so I learn? So a twin is a living learning model. It keeps itself up to date. It learns from the fleet. It learns from itself. It learns from simulations. It learns from humans. But what does it learn? What can it tell me? Because it's a representation of the state and it's telling me things, it gives me insights. Can I detect a failure earlier? Because if I can detect the failure earlier in a jet engine, what I do is I can detect it a month earlier because I know one of the bearings is going to fail. Well, guess what? I can actually get that repaired and I don't have a situation where at the gate, all of a sudden there's a light that goes on and you say, well, everybody has to deplane. So I can do early detection of failures. Can I predict, what damage will be at the end of a year? And so I know what parts to have ready so I can quickly repair it. Can I predict the demand that I would need given the weather conditions and what I've seen over the last few years? What's the demand for electricity that I would have? Can I optimize operations? Can I actually look at that and say, is there a way for me to optimize how much fuel I can use so that I can produce the most electricity with the least amount of fuel and so lower the cost of electricity, especially in places in which there are emerging economies? So those are the insights I get out of digital twin. So that itself is thinking about the business model. Now that I have the business model, what do I do? Because if I have these insights and I can't do something, it's not useful. These insights sitting on a shelf, no good. Now I drive work. With the insights, I can get work done. I can actually send work to the control system. So the controls, if you're optimizing something, can adjust in the turbine, the amount of water. They can adjust the airflow. They can adjust, the fuel flow in order to optimize the fuel so I can deliver more at lowest cost. I can send it to a human in a human control system for a grid. And that human can say, well, the demands I'm seeing here, you know what? I think we'll have to actually get some other sources online. Or I can predict that this system looks like it's in trouble and it's going to be dropping the ability to produce electricity by 10%. Maybe I need to go find it in some other sources. Or I can do automated repairs. I can say, you know what? I can detect that failure early. So let me send either a human out to do it or send a robot out to actually do a repair for me, or a robot to actually do an inspection so that I can get a better idea of how severe that failure is going to be. So this is where you go and you got the digital model or the business model, the twin, giving you insights, and then you got the delivery model or the operations model doing the work. And as the work gets done, you feed that back in. That's more data coming in. And as you feed that data coming in, the twin gets better because you did the controls. Well, am I actually getting better fuel? If I'm not, let me optimize that model. with the human controls. Did I take the right actions? If I did and it worked this time, well, let me make sure the twin knows that and we can continue doing it. So that's that loop in which you're seeing the physics and domain knowledge with the data and machine learning get the twin to give you insights to do work to get value. Now here's the other loop. After I do that long enough, I get information that allows me to do better designs. So what we learned from having digital twins on our aircraft, we believed initially the greatest stress on parts inside the jet engine was when you climbed, right? When you actually at one level, you're at 5,000 feet, you climb to 8,000 feet, that should be the greatest stress. And so that's how we designed, some of the parts. What we found by this flow of information is the greatest stress usually occurs on takeoff, especially if you take off at certain angles with certain power. And so now we can use that to actually get some design feedback. We can change the design of those parts so that we can make those parts last longer. So this is this digital industrial transformation. It looks very similar to what you saw in consumers, right? Finding value with a demand model and then, or a value model, and then delivering that value with an operations model. So good. So now where do we see this working? Let's talk about that. Let's go to aviation. Let's talk about how these digital twins actually deliver value. So let's talk about three things, because when we think about value, we go to a customer and we say, what can we do to help your business be more valuable? First thing is, can we give you sufficient early warning? The worst thing you can do is arrive for that flight. You're trying to get on the flight, all of a sudden they tell you there's a maintenance problem. Okay, no, nobody's on that flight. Right away, 300 seats are lost, right? Because again, that's time. So yes, you can move people onto other airplanes if you can, or maybe delay a few folks, but that plane itself does not take off and there's a significant, loss of revenue and profit there. In addition to literally pissing off your customers. So what do we do with a digital twin is we take the physical understanding we have together with the data. So we can take physical things like the compressor pressure, temperature, the exhaust gas temperatures itself, look at the data we have and then predict the probability of failure, because we also look at the routes it flew, the way it was flown. And once we predict that route of failure, we can predict these compressor issues 30 days in advance. And you need 30 days to allow you to actually replace that airplane, those engines from actually, being there for that flight. That's early warning. Continuous prediction. The other thing we want to do is, how do we look at damage? So here's one of the things that we found out. When you fly in hot and harsh environments like you do when you're flying into the Middle East, two things happen. In many cases, because of the heat and the sand there, it lands on the blades. What happens on the blades itself, it damages or removes that coating on the blades. You expose the material on it, and that causes severe problems. And what was happening then is that was happening so often that we didn't understand it. So we would have to, every 200 flights, bring the assets in, bring the engines in and inspect them. That's taking away the asset from the customer, so reduced availability, and also, putting the customer through enormous distress. Because in many cases, if you couldn't fly that plane, you have a bigger problem. Customers say, let's move to a different airline. We don't want to use your airline. So what we did is we built a twin that could actually understand, based upon the environments you flew in, what city pairs. If you're spending a lot of time flying in the US, it's not a problem. If you spend a lot of time flying into China, parts of Saudi Arabia, into new emerging countries in which there's a lot of building and there's a lot of contamination in the environment, could be a bigger problem. So we figured out the city pairs, we know the temperature, we know the humidity, we knew the contamination level, and we built a twin. What that twin does is predict the damage on that blade. Here's what that does for us. It means rather than bringing it in every 200 flights, in which in many cases we're looking for something and it's not there, now we have the ability to say, based upon where it's flown, don't bring it in for another 1,000 flights. That's okay, because now the availability is higher, the customer has the asset, and that's perfect. Customers are happy, end customers are happy. And by doing this, we saved a significant amount of money, $91 million, in 1 year alone from doing this. The last thing is dynamic optimization. How can I actually look at your fleets and tell you when to bring in different aircraft in such a way that I have the least amount of aircraft being serviced, and to allow you to make the most money from those aircraft? And that's what we're doing. We're looking at the damage in every aircraft, figuring out when to bring them in such that you can optimize your fleet. And if you do that right, you know, the ability to lease, because when you bring something in and you don't have an asset, you have to lease another engine. So now I can reduce my leasing cost. So this is how you actually use that data to understand the value and then to deliver the value, using insights and allowing the insights to drive work actions, you know? So now when you think about that, you think about there's value. So now how do I encourage people to actually use these things? Because the minute you say it's digital and using AI, people get upset. They say, well, you know, AI is a black box. I don't know what's really going on. So now we've begun discussing what are the ways after I've shown them value to encourage people to deliver value. So always think about that, right? It's not just about can you deliver the value, then you got to have people actually adopt the value. Now I'm going to take a different example to show you what we did. So this is in the energy space. So we have the ability to generate, as I talked about, early warnings. We can actually look at the data that's going on. We take the data of the environment, we look at the sense information, and we can predict that things will fail, right? And by doing that prediction, you know, we can go out and repair. Now, when we go out to repair, we send a human. So what tends to happen? Let me explain to you some of the repairs before. It was really manual, really tedious. An engineer would go out to this tall wind turbine and would go in, and maybe there's a problem with, you know, we've seen a lot less performance. The energy that's being produced from the wind turbine dropped. So the engineer goes outside and runs a bunch of scripts. The scripts actually give it information. The engineer looks and sees things, but then it says, all right, you know what? I'm going to try to figure this out by plotting graphs. I plot a graph of the wind speed against the vibration of the tower, or the wind speed against the pitch of the blades, or the wind speed against the output. And then what I do, because all of that has to be done at the tower itself in many cases, then what I do, because it is a little computer system there, is I look at graphs. I say, give me a graph of the wind speed, 4 or 5 graphs of wind speed against, you know, vibration in tower, wind speed against pitch. And then I look in my manual. Once I get that graph, which is what you're seeing there, these little blue and gray things, I look at my manual. That manual has a troubleshooting guide. And I try to match up and I try to say, well, which graph that I have now looks closest to what's in the manual? And once I find that, I get the answer. If it looks like number 1, well, it's much more potentially, you know, a sense issue. If it looks like number 2, it looks like a pitch angle issue. If it looks like number 3, it's a control issue. If it looks 4, it's a gearbox issue. And that's how they literally do it. They go out there, they take measurements, you know, in a fairly dangerous environment, in a fairly harsh environment. There's wind, and some of it is in areas in which it's very remote. And you actually then compare to the manual. What if we have a computer system, an AI system, that you can send the engineer out there, because in many cases you have to access that data. But while it does that, the system looks at the graph and uses a deep learning engine and tells the engineer, I think it might be number 2 or number 4. The engineer still has to do the work. It still says, well, all right, let me check, because you always want the human there for verification, because we are dealing with things that are hundreds of millions of dollars. In many cases, you know, lives matter. So you have that verification, but we have now built a way that we call explainable AI. I literally can explain to you, the AI system says, I chose these 2 things because they look like what you have in your troubleshooting guide. So this is the journey we've been on. Not only do we deliver value, but how do we explain the value? Let me tell you another journey we've been on here. This is another interesting one called humble AI. Because as I say, every time you say you can deliver value with digital, you know, capabilities, people say, well, I'm not sure. How do I help with business adoption? The first was explainable AI. Second is humble AI. Here's how humble AI works. You know, this is where every model you built is built on data. All the data that you have is what you use to build that model. And what you tend to find is that people tend to have a lot of data based upon things that occurred before. So what we've often seen in GE is that, well, initially during the design or during some problem, you know, we went out and collected a lot of data on wind speed. Wind speed at a certain type, it's between 7 and 10 meters per second. And that's important because once you understand what type of data you have, then you can understand the value of your model. Now, why is wind speed important and why it's time of year important? It's because of how the wind works. So what this diagram here is showing you is that wind speed varies a lot. Wind speed varies because you're seeing, the wind speed varying over 24 hours. The wind speed at a location in front of a turbine changes every hour. The winds go up, the winds go down. Here's the other thing that happens. It changes seasonally. Every 3 months, the wind speed varies at a different time. The wind speed also is different at different heights, right? At 22 meters, 80 meters, and 138 meters, the wind speed is very different. So imagine, you've created a model, but you have to understand where is that model most convenient because this thing is changing all the time. So what we do is we say, is there a region of competency? If I have spent a lot of time to get this data, and the model is going to be best at the place where I have the most data. That's called a region of competency. In this illustration, between 6 and 7 meters per second, we had a lot of data, so that's where the twin operates very well. Now, outside of that, the reason it's called humble AI is outside of that region of competency, the AI system tells you, I don't know a lot about that. Why don't you go back and use a human or go back and use the deterministic algorithms, right? And then give me more data so I can learn. So the AI is humble. It knows what it's good at. It knows the zone of competency it's good at. And outside of that, it actually lets somebody else do it. And this is what business people love, because now I'm not taking a risk. I can say, well, okay, it makes sense. I'm going to start off my business process in a very small area. I'm going to see how well it does. And if I like it, I'm going to expand it a little bit. So this is the notion of the region of competency between 6 and 7. Outside that region, when you get outside of 6 to 7, right, you go back to a regular algorithm that you have. And the twin says, give me more data. I want to learn. It's a good student. And that is the notion of humble AI. And then over time, what happens is you go from 6 to 7 because you're giving it more data, the region of competency gets larger. And so it can do more things. At the same time, the humans get more confident about it. So that's the improved use. And we have this deployed in quite a few wind farms right now, getting better and better and watching the human response to it. So those are the things. The last thing I'll talk about, because this is the other thing that I love about my role, because in my role, I do things that deliver value. I do things that are new, cutting edge, like humble AI, but I also do things that are very different, things that are going to change the environment. Here's a new one we have, right? This is called an emerging language. What I'm trying to do here is the idea we thought about 5 years ago was, what if wind turbines could talk to each other? What if they have a language and they could talk to each other and explain to each other the problems they have and then suggest what the problem is to us? So when the field engineer goes out there, the field engineer will say, well, the wind turbine said it was really either a pitch bearing problem or a controls problem. So I know I don't have to check 10 things, I'll just check those 2 things. And that's the journey we went on with some very interesting DARPA grants that we got. Now this looks complex, but let me tell you what's actually happening here. So when you look at this wind turbine here, right, we created, let me start with this diagram at the top. If you look at the one at the top here, wind turbines give you signals. What we found a method to do by using convoluted neural networks is to find a dictionary, right? So for instance, the dictionary is a way that the wind turbines can create a language between themselves to express certain things. Again, this is very original work, and we've now begun testing it in one situation. Here's what this means. If you look at the top, you will see things like wind and an up arrow, right? That's a symbol indicating, well, wind speed was increasing. And then you see this blade and there's damage on the blade. That's the 2 things you see up here. And then there is what looks like a signal, which is vibration. And then you see electricity and you see a down arrow, which means electricity is dropping. So it's a simple sentence constructed by a wind turbine that somehow said the wind increased, there was damage on the blade, you can detect it by these vibrations, and that caused a drop in electricity. A simple concept, very hard to get to, but a simple concept. And we have been using these neural networks to define the way to do this kind of language. And we've made up one in which, the wind turbines can describe wind, they can describe energy, they can describe increasing or decreasing damage blade, they can describe things like ice. right? In some cases, you'll say there was wind and ice, which is usually a windstorm at wintertime, and that caused damage, and that showed a reduction in electricity. And so we have been playing with this. And if you want, I can give you a great reference where you can read the paper. And what we've created out of this, it's two neural networks with a couple of encoders and decoders. This agent was able to generate some meaningful language. It's a turbine language. And in the turbine language, the turbines say there's a problem. Now, even if the turbines figure out a problem, how does a human know it's a problem? So then we use some really interesting translators. We can use a translator, and a translator is something simple. So for instance, we can give a wind turbine a known problem. We can actually put it in a way where, we have slowed down a wind turbine during, maybe a major storm. So we know damage is happening at this point in time. And we can actually look at what it's telling us, and we know damage did occur. So it's trying to tell us that. And we build a human translator to say, I can translate between what the wind turbine is saying and what the human is saying. And so we have been experimenting with this in DARPA and seeing some very unusual results. This is a journey that will take another 5 years, but it's a journey in which we begin to see the power of what could potentially happen here. So if you look at the track that we went on a track of looking at what were the forces shaping the world to know that what we will work on will be ready and will be willing and needed for the next 10 to 20 years. Then we talked about this model, this notion of data to give us an idea of the business value, and then data and software to help us deliver that value. And we saw it in the consumer space, and then we took it all the way into the industrial space using a digital twin and a digital operating model. Then we showed that we can literally find ways to create value, which is the business model, and deliver the value either through doing repairs better, optimizing the asset. Then the discussion was, now that we have that value, how do I actually help it become more and more useful? So I have things like explainable AI. This will actually allow businesses to trust the AI system. I have things like humble AI. This will allow the businesses to say, okay, I have minimal business risk, and let's adopt it. And then we talked about emergent languages. How do we actually think about the future, a future that you can build for us? Using things like emergent language and the new work that's coming out of DARPA with AI systems. So I hope I've taken you on a journey that actually showed you how these digital transformations are transforming and shaping my business for the future. I want to leave you with one last slide. I think it's only useful if you have some thoughts for consideration when you spend 45 minutes of your time. And so this is a sort of framework I'll give you. Right? And it's a framework that's applicable to any industry you're in, not just the one I showed you. I think the first thing you want to look at is understand the forces shaping that market. When you go into a market, make sure you know what those things are and if it's going to last 10, 20, 30 years. You'll need that because of the profound work we do as engineers. It takes time. You're not going to do something profound in 2-3 months. That just doesn't exist usually. So understand the forces shaping the industry, whether it's the customer demands or the government demands. The second thing you want to do is look around for what other people are doing with their digital operations models and their digital business models. Understand those. Don't try and build those from scratch, right? Figure out what others have done and use it. Use it. Legitimately use that and build upon that. It will save you a lot of heartache, it will save you a lot of money, and it will accelerate your progress. Third thing is understand the transformations that are happening. So even while you're doing that, think about the technology. We talked a lot about technology, but at the same time, to get the money out of this, the business process has to change, the organization has to change, the people you hire have to change. How do people think about this has to change. So it's not just that I produce my technology and once I have the technology, that's it. No, you actually have to then convince people to use it. That's what I was showing you with explainable AI and humble AI. You have to get inside their business processes and know they lose money when a jet engine can't take out. They lose money by using too much fuel. They lose money when these wind turbines aren't operating. Understand the business process and the org. And then the fourth thing you need is yourself. This is self-reflection. What do you need? What do you need to go on this journey? This is a journey of multiple years, multiple decades. First is awareness. If you aren't aware of the forces and other things that are happening in the digitization things, you're going to miss it. The second is resiliency. We build things, which means we are going to fail. we most likely will fail more than we succeed. So as you fail, you've got to step back up and be resilient. You've got to say, well, I don't care if I fail, I'm going to do it again. And the third thing is learning. You're going to have to learn. And this is not just you learning, you have to build your learning networks. There are things that I don't know that I reach out to Valerie. Valerie's an expert in certain things. I can get it from her. I don't have to learn everything. I just have to learn some things, and I have to learn who else is learning and reach them. So I leave you with these 4 things for consideration. I leave you with one last thing. I have been wrong in many things I've thought about, right? Which is where I get my resiliency, right? I never believed this cloud thing would have taken out. It took me years to realize that I thought computing would all happen on premise. I was wrong. I believe that, guess what? I would always own my data and never share it. I willingly share my personal data with Amazon because that's how they give me information, right? I listen to, customers say that they want products. Now, the most important thing are services. They buy the products, but they always ask about the services itself. So there's a whole bunch of things that I thought would never happen. From that, I've learned that, well, Colin, you're going to be wrong a lot of times. Be open, be resilient. The other thing I found out is that I have the ability to predict the future. I know it sounds, strange, but I'm going to give you an example of the future I'm going to predict just for you, just for this team. Here's the first prediction I have. Be prepared to write this thing down because this is profound. First prediction I'm going to make is I will get older. That wasn't that hard. I make the same prediction of the machines that GE has. The machines get older. It's not hard to predict that. Here's the second thing I'll predict, just so you see it, right? No customer is going to pay me more. So I produce a product now, next year I go to the customer and they've bought the product this year. Next year I go to them and said, I love your product. I'm going to give you more money for that. No, they always want it for less. And the third thing I'll predict is that this change will perpetually happen. It wasn't that hard to predict the future. Things will get older. They will want to pay less for them. Change will happen. Be prepared. This is the journey you need to be on. So with that, I will stop. I hope I used your time wisely here. Again, it's been my honor and privilege to spend time here, and I look forward to meeting and working with many of you in the future. With that, I'll turn it back to Valerie.
Okay. Thank you. And so one question we'll start with was that looking at the forces, one question that came up, and that is the role and the importance also of addressing climate change. And that is, you talked about carbon neutrality, and I think here the question related to climate change and also its impact on profits with respect to companies, and if you could provide your insights there and comments.
So I'll give you my personal insights as well as GE's insights. Climate change is very, very important for us, right? And so what we've been doing is we've been working actively on a lot of the net neutrality. We have a huge division, an $18 billion division on focus on renewables. And for us, renewables are wind turbines, hydroelectric systems, batteries. And those are the things we focus on and how you tie them together into systems. Now, while we do that as well, we also, look at what's actually going on in the world. So for instance, we have coal plants, we have natural gas plants, and we have renewable sources. Renewable sources are right now 8 to 11% on the planet. There's still quite a few things that are happening with the coal sources that we have to get out and the gas sources. We would love to actually say, let's all revert to using renewables. However, the actual running of countries, requires that there is this energy capability, because that same energy is what's being used to actually take people out of poverty, run hospitals, do everything you need functionally. So there's that balance that you got to look at, and you have to have a plan by which you literally, determine how are you going to do that transition. And there's a couple of ways to look at it. So for instance, there's one thing to say, let's go entirely to bring in on new sources of renewable energy. But what you do find also is that the grid is very inefficient. Right now, could we actually gain efficiencies in the grid itself? And so use that to actually turn off some of the coal plants that we have. Can we actually do things around, we have a lot of other sources. We have energy stored in batteries in a variety of places. We have energy stored in a variety of other instances in which we could actually use that and put that into the grid, and the grid could use those sources, except right now, there isn't government regulations that will allow you to sell that. And so those folks who have that capability, they may do it for a company they have, or they may do it for a certain focused environment, maybe a microgrid. But if you can actually have the government legislation allow them to sell it onto the grid, now you have a marketplace in which people are going to invest more and more in batteries, more and more in alternative technologies, more and more in efficiencies to go after, the reduction of carbon. So the journey for the carbon reduction is not just simply a journey focused on let's just get rid of one set of resources. It is back to the discussion we had before about constraints and balances. You have constraints in that people are asking for energy. We see in many places, I could cite a good few in which we've seen literally countries be destabilized, elections be stabilized because of lack of electricity, right? You go to certain parts of the world and they tell you directly, if I can't get a stable source of electricity and healthcare, this government won't last more than a year. And so they will do anything to get that stability. So now you've got to match those constraints with what we have. Can we produce a lot more renewables in time? Maybe. We can, we're doing that, but can we actually look and just get efficient on what we have? Use less power, use the sources we have, and balance that out. And that's the journey we've been on in GE. We've spent time with the World Economic Forum on this. We've spent time with other people in the industry. So it is one of the most important journeys for us at this point in time. We're doing it even now in aviation. We're finding the ways to design engines that produce less carbon, or ultimately no carbon, as they fly in the atmosphere. So this is a major journey for us, but it is a very, very complex problem involving not only the technical aspects of it, but the governmental aspects and human aspects.
Thank you. And that question was from Pedro. And we have another question too from Peter Sergey, who was asking a question about sensors. And if you could comment on what are the types of sensors that are needed to go with the turbines, or different devices in terms of the data collection.
Yeah, Peter, that's a great question. That was an interesting thing that I learned when I first joined here. So we saw sensor costs drop. And so it's easy to get these very small, very useful sensors that are low cost, and you can put them in many environments. So if you have a plant that's new, you build all those in. So that's a given. And you get more data can create better digital twins. Now, I walked into the environment inside GE Aviation, and then to my shock, we have one of the best engines in the world in the GE-90 engines. And then, so I said, well, how many sensors do you have? Because I want to collect all that data and I can build you twins like you wouldn't believe, right? And I'm thinking, all right, we got at least 6,000, 7,000 sensors on these jet engines. And the answer was 21. And you say, why do you have 21 sensors on a whole jet engine? Well, then you find out the cost to build one sensor is roughly $25 million. Why? The sensor has to operate on the ground. It has to operate at 10,000 feet. It has to operate in temperatures that go between minus 300 degrees, because it's flying up there, to all the way, minus 100 degrees. It's flying in certain parts of the atmosphere where it's ridiculous, to where it's landing and it's 160, 200 degrees in that environment. The inside of the jet engine gets to 3,000 degrees. It has to operate for 40 years. That's the life of those planes. And you'd like to sense that the life of those engines, you'd like to sense it to last that long. That's why you can only have, 20 something in each of these aircraft. So that was one of the biggest things, that was amazing to me. So what we had to do was we had to create virtual sensors. So here's where, if I have two sensors that are separated by, 5-6 feet, my worry is what's happening between, what's happening to the materials or the space in between those. How would I determine that? Well, one of the ways we create virtual sensors is we have these huge test beds in which we take apart an engine, and we try to understand what's going on in the middle, and we have this running engine. We may actually, because we own it and we have this massive test bed, we can put paint or special kind of paints and run that engine, get to that heat, watch the color of the paint. And so by having a computer vision program, watch the color of that paint, I get a view of what's happening there. So that's a virtual sensor. I could also go in simulators, and I actually run the simulators, and the simulators try and simulate using physics what's going on between these 2 points. And I create a good enough virtual sensor that I say that's good enough. And then when I bring in the plane with the engine, for inspection, I look at the material between those two and I say, it was a lot hotter than I thought, and I calibrate the sensor. So we have been embarking on a process of where you can put in, more sensors on new things, put those sensors in. Where you can't, create virtual sensors using the data that we have, using the simulators that we have. So that's the journey with sensors. So think always both about more physical sensors, but maybe more virtual sensors.
Thank you. Yeah, I didn't realize it was the sensors were so expensive. So thank you for that.
I know.
Yes, because I was here thinking too, a large number of sensors, but when you brought up the cost, it really emphasized the small number of sensors. One question that's come up too across multiple attendees, and that was the engagement of humans or people within the overall system of working with digital twins. I think it was raised when you talked more about the humble AI, because then you're looking at, what is the area for which there's great confidence in the results from AI, from the AI models. But then if you can talk about it overall in terms of how, people are involved in those, in the overall system. And I know they're involved in terms of the decisions, but just the role of people in this with digital technology.
That's a good question, Laurie. I think the role of people are quite profound, right? So they, so people obviously have to build the twins, that's given, and people work with the twins to achieve things. And in many cases, people think that, these capabilities will remove people from jobs. There are two categories here. One is there are situations in either dull, dangerous, or just destructive environments where you want to move people from those jobs. And so where you want to actually have digital capabilities. On those wind turbines, we are now using drones to try to examine the blade. Because what you have to do is you got to go and look along the length of that blade. That thing is 200 feet high. Each blade is 100 feet in length. Right. What we do is either we try to get helicopters to move around where people try to inspect that using cameras, or we hire people who are really good at mountain climbing and they go up there. The problem is, as we said, the wind can change direction or speed at any time, and you're putting lives at risk. So we have many situations like that where we're trying to get people out of the way and not have them do those type of things. So that's one in which the AI can remove the person entirely. Then there's a category in which the AI, when I think about AI, people think artificial intelligence, I think augmented intelligence, right? It's the same discussion right now where we're having with the radiologists. When a radiologist is looking at your lung, the AI systems actually, do two things. They can come and they can do what is known as guided, which is they just show the entire lung and they highlight major spots in which the radiologist should look first. Or they can do what is called assisted, which is they don't highlight the entire lung, they just highlight the 4 places that the radiologist should focus on, and the radiologist focus on that, right? Both serve different purposes. One is to highlight everything and focus the radiology so that the radiologist can do more of those. And the second one is when the system is smart enough, what you want now is the radiologist really focused, because maybe that radiologist is looking to tell the difference between something that's cancerous and not cancerous, right? And so you have to be really precise at that point. So a lot of the cases of the AI is where we're trying to involve the humans, and rather than have humans do average work, can I get either the human to focus in an area that I can maximize the value, or do I have something so complex that I know there's no way the machine could figure it out, but I want the human to try and sort through the complexity in that area. The problem we have is we keep thinking that it's just replacing jobs. But the other thing we never think about is that, do you see how complex society is getting? We talked about decarbonization. To do that right, you're going to have to combine a wind turbine, solar, with batteries, with a gas turbine, or even a steam turbine all together, because all of these things are running. And you're going to have to decide, when do you want to turn one thing on, turn one thing off? Maybe at times when there's no wind or solar, right? Some bad days, there's no wind, there's no sunlight. You got to turn on the gas turbines. Well, okay, how do you figure that out? Or maybe some days when everything is going well, you want to store some of that excess in the battery. Think how complex that equation is. Think how complex that is. Do we have humans who are going to figure that out by themselves? No, they're not. So you need an AI system and these kind of systems to guide you through that. So the AI is augmenting the human in many ways because we are building ourselves into a very complex society. And as the complexity rises, the humans have to rise with the complexity, and it's really hard to do it all by yourself. So what you have is that AI, augmentation, tying these things together. So think about it that way. We're trying to use the AI to actually, and we are building the AI, right? It's not building itself right now as yet, but we are removing humans from dull, dangerous, deadly jobs. And we are also having the AI help us when the complexity is rising at a rate in which it is just hard to contain because of the things we're putting together.
Thank you. And we have time for one more question. And that question I'll take is from Jonathan. And the question has to do with where you were discussing the languages with the turbines. And that is, you were looking at the emergent languages. And the question that came up is there also communication among the turbines such that they're communicating with each other to do some detection among the turbines about different aspects, not just conveying that information to, let's say, the operator or the engineer?
Yes. So I wasn't too clear on that. The turbines are talking among themselves. See, because we built a language where they can talk among themselves, right, and determine problems themselves. But the next step after you build a language is you've got to figure out how do they actually collaborate, right? It's like humans. Valerie and I can build a unique language and we can talk at length, but we can just talk about anything. Now, the next thing to do is how do you actually get them focused on, well, let's talk about a specific thing and try to figure out a specific thing, which is really about cooperation. So on top of that notion of the communication, there's also DARPA grants. One of the well-known ones is CREATE, C-R-E-A-T-E, that actually talks about how do you actually then collaborate. So what I have hidden there is not only the work on creating the communication language, but also creating the cooperation so that you could actually say, why would you cooperate? Because again, it's not a natural thing. We humans take it for granted we cooperate because intrinsic in our minds is a notion that, well, if we cooperate, I'm going to get something, you're going to get something. Machines don't. So you have to find some way to give it an objective task that says, well, if I cooperate, I'm going to get information. And if I get information early enough, it's going to help me at some time in which I'm going to avoid a defect. And so my overall electricity that I'm producing over the next 4 years is going to be higher. So you've got to find some weighting or some objective algorithm that sort of drives cooperation. So you have both in it. You have both the communication and the cooperation aspects of it. And that's why it gets hard because, again, you learn a lot when you fail. And so you've seen we've seen in this, we do it in simulations. We don't do it on the wind turbines all the time. We do it in simulations. You've seen some interesting things where you ask them to collaborate, and for whatever reason, they collaborate by all speeding up rather than finding a defect. And then is when you realize, well, I don't fully understand this, and we go back in. Or basically the algorithm you've given them or the objective function you've given them forces them not to collaborate. You find groups collaborate and groups don't. Or they suddenly form, and this is the bizarre thing, they suddenly form groups that are collaborating within themselves and competing against others. So this is a lot of learning as we begin to flesh through these things. And again, the reason I bring that up is because always think this is a decade-long journey. What we do here as scientists is profound. And when you do profound things in things that matter, because you have lives at stake here and you have billions of dollars at stake here and the planet at stake, you want to really test this thing out. But you have to start on that journey because, the real key breakthroughs don't happen because you've spent 2-3 years doing something. It takes decades to actually make this worthwhile. So that's the much bigger picture.
Thank you. And thank you, Colin. That was an excellent talk about digital technology. I think it's really exciting to hear about the value creation, about the use of technology, and also the importance of the creation of technology. and I think from multiple aspects. And so it was wonderful also to hear about the examples with GE Digital. So I want to take this opportunity to again extend a thank you for a very engaging, enlightening, and really exciting talk about digital technology. So a virtual thank you.
Thank you. Well, Valerie, it's my pleasure, my honor to be here. I'll leave with one last thing though. You know, my time is nearly over on this in the sense of, you know, I'm older right now. So I'm looking for this generation that you have here and these people on the phone to build this future for me. And I do want to find a way at some point in time to take a journey into space. So I'm depending upon this institution to go drive that for me. So, because I know you have great talent here and I can see it already. Valerie, thank you for the time. Thank you all. Have a great, you know, time and be safe. Bye-bye.
Thank you. And so I now turn it back to Rob to conclude our morning session. So Rob?
Thank you so much, everyone. Thank you, Valerie. Thank you for your great questions. And thank you especially to Colin for a really engaging and great talk. I have a couple of quick housekeeping details. First, my apologies for a glaring omission earlier. Quincy Brown served as our general chair this year, and I am so grateful for her leadership and for all of her hard work. Thank you, Quincy. I hope you all have a wonderful day. Enjoy the day.